Colour. Wherever we are, it controls our actions and attracts our attention. Colour brings beauty into our lives and creates an atmosphere of peace. Today, this wealth of colour can be seen on the television screen. The first thing to observe is that all colours on the screen are made up from only 3 primary colours. These are different from the primary colours used by artists and printers because the process that occurs when pigments are mixed is totally different from the process of mixing light. With the familiar method of mixing pigments, it will be noticed that yellow is one of the primary colours. The mixing results are due to the absorption of light by the pigments. When the 3 primary colours are combined, light absorption is maximum and the result is black. The process of mixing coloured light is totally different. Here, the primary colours are blue, red, and green. And when mixed, results are, for instance, cyan, purple, and yellow. Mixing of the 3 primary colours results in white. In this example, the mixing occurs by overlapping colour spots, but the same visual impression can be achieved with separate spots, provided they are sufficient in number and very small. When the dots are so small that they seem to merge, mixing occurs. This merging dot method is frequently used in colour television. In the picture tube, the screen is completely covered with small luminescent dots which radiate in the primary colours. These phosphor dots are so small that they can only be distinguished with the help of a magnifying glass. By varying the intensity of the 3 primaries, an endless number of colour shades can be obtained. Now that we have seen how any colour impression can be simulated from 3 basic colours, we will examine the method by which colour pictures can be transmitted from the studio. Upon entering the camera, the multicoloured light will be divided into 3 parts, each part corresponding to one of the primary colours. This is achieved with an optical system comprising 2 colour selective mirrors and 3 separate camera tubes. Let us start with the blue part of the light. The rays strike a mirror reflective exclusively to blue, then, via a second mirror and a blue filter, passed to the upper camera tube. Now, the red light rays. They pass straight through the first mirror, are reflected by a red selective mirror, and enter the lower camera tube. Finally, the green light rays. These pass through the blue and red selective mirrors and enter the middle camera tube. Let us examine further the blue component. The camera tube transforms the light into a pattern of electrical charges, which are scanned electronically. This repetitive scanning results in an endless succession of electrical impulses, the picture signal for the blue component. The same procedure occurs for the green and also for the red. In this way, the camera divides the light into three components and transforms it into three electrical signals. These may then be conveyed by a cable to a picture tube, which we will discuss in detail later. Each signal activates its respective phosphors on the screen. One signal the green phosphors, another signal the red, and the other the blue phosphors. As in fact the three pictures are superimposed on one screen, the three colors combine again. Mixing takes place, and the original image is obtained. The system in which the signals are conveyed to receivers via a cable is called closed-circuit television. This system can be used to advantage in industry and science. Before considering the wireless transmission of color pictures, we will examine first the method of transmitting black and white pictures, because a similar method of transmission is used for both systems. The black and white camera shown transforms all the light into one signal, which is then conducted to the transmitter and transmitted by an electromagnetic wave in the form of amplitude modulation. A similar picture signal will also be found in color transmissions, and it is this similarity that makes the two systems compatible. Consequently, the picture signal is not only received on black and white sets and transformed into the familiar black and white picture, but also the color receivers are able to receive this signal. Since this transmission comprises no color information, the three phosphors radiate constantly in such a proportion that only a black and white picture appears. Over now to the color transmission. In the camera, as we have seen, three primary signals are produced. In order to achieve compatibility with the black and white system, the primary signals have to undergo some mathematical operation. They are conducted to a circuit where they are added together. This occurs in the following way. A more or less bright part of the green component provides a corresponding output signal. The red picture component does the same, and similarly the blue. If two or three signals enter the circuit, the output signal will consist of their sum total. This signal is called the luminance signal, and the fact that it is the sum of the three color components means that it represents the total light that entered the camera. Thus, the luminance signal is similar to the picture signal produced by the black and white camera. It is also transmitted in a similar way. There now remains the question of transmitting the color information. In parallel with the adding circuit is another circuit, which extracts the necessary color information from the primaries. In this example, only the red and blue signals are used. In order to transmit the color information, a sine wave oscillator is used to produce a sub-carrier signal, and this is modulated with the color information. This modulation process is represented here in a simplified manner, the technical details being beyond the scope of this film. The modulation of the subcarrier gives us the required independent color signal. For transmission, the color signal and the luminance signal are both modulated on the same electromagnetic wave. Black and white receivers utilize only the luminance signal. But we will now see what happens in a color receiver. Here, after the tuning and amplifying stages, circuits are present in which both signals are regained, the luminance signal and the color signal. Further circuits are used in which the signals undergo a mathematical change, this time to regain the three primary signals. Let us first take the color signal. From this, the information of two of the primaries may be extracted, in this case, blue and red. But how then can the green information be derived? We have already seen that the luminance signal is the sum total of the red, blue, and green. Therefore, if we take only the blue and red signals and subtract the blue from the white, we obtain yellow. And red subtracted from yellow gives green. In this way, the three original color signals are reobtained. Now we come to the actual reproduction of the color picture. This is achieved in picture tubes such as the shadow mask tube shown here. Unlike the black and white tube, which contains one electron gun, this tube is provided with three guns, each of them producing an electron beam directed towards the picture screen. One gun for the green component, another for the blue, and a third for the red. In fact, the three guns operate simultaneously. Let us consider for a moment the electron beam for the green component. Its path ends on a picture screen which is completely covered with luminescent dots of the three primary colors. In order that this beam activates only the green dots, a perforated mask is used which prevents the electrons from striking the other color dots. So only green is activated. For simplicity, we will show just one spot. The gun for the blue component is placed somewhat higher, so that its beam, passing through this same hole in the mask, strikes only the blue dot. The third gun is placed so that its beam will strike only the red dot. All parts of the picture tube are positioned with such great accuracy that each beam strikes only its relevant dots. Just as with black and white television, the electron beams scan the screen in a constant rhythm, at a speed that gives the impression of a constantly radiating screen. Now for the picture. As the three color signals obtained by the receiver vary in amplitude, they cause the three electron beams to vary in intensity. And it is in this way that the brilliance of the colors is caused to vary. Three primary colors that for our eyes evoke all the colors of the spectrum. The colors of life. Color television.